Hello. These notes are going to cover 8.2, area of a sector. Last set of notes we talked about was arc length. And when we talked about arc length, we said that the arc length was part of the circumference of a circle. So we were able to set up a proportion. And then today we're going to be talking about area of a sector. Sectors are part of the area of a circle. And so again, we'll be able to set up a proportion today. Formulas are pretty similar, which is awesome. So it says a shaded portion of the circle below is known as a sector. Sectors are a small portion of the circle's area. Therefore, we can set up a proportion to find the area of a sector, okay? So this shaded portion right here, this thing right here, this pizza slice, if you will, is known as a sector, okay? And we want to find the area, how much space that takes up. We find that by doing our central angle over 360, because there should be an angle there. Okay, you should have an angle at some point there. So it's going to be the central angle over 360, and that's going to equal our sector area over area of a circle, which for us is pi r squared. So again, it looks very similar to the formula from the last set of notes, but instead of it being over circumference, it's over area. That's literally the only difference. All right, so here we go. We are given circle O. This is actually the same problem as last time. First thing it wants us to do is find the area of the circle. Area is pi radius squared. So my area is 144 pi. I'm going to use that when I go to find the area of the sector. Now, I do want to point this out really fast. It says area of sector AOB. Even though it uses 3 letters, it's doing that to show you what the small sector area is, okay? If I want you to find the large sector area, we're going to do something like this, and we're going to shade it for you. So when it says AOB, even though that makes you think it's the large sector, it's actually the small sector. So AOB is this thing. Okay, I'm looking for the area of that sector, that pizza slice. So it is the central angle over 360, and that's going to equal my sector area over the area of my circle, which I already found. I already found that that was 144 pi. So we're going to cross multiply. We've got 60 times 144. We divide that by 360, and we get that the area of sector AOB is 24 pi meters squared. There you go. That's literally all it is. Let's come over here and look at this one. We need to find the area of the circle. And again, we're finding just the total area on this one. So that's going to be pi times our radius squared. So that is 81 pi meters squared. I definitely didn't put units on this one. Meters squared. And then again, I'm going to use that whenever I go to find the sector area. Now this one says, what's the area of the shaded sector? That's the wrong color, the shaded sector. So that means that I need this central angle, which should be 320 degrees. So we've got 320 over 360, and that's going to equal x over 81 pi. 81 times 320 divided by 360 is 72. So this will be 72 pi meters squared. Okay. Now we could double check this, and I want you to compare that to the total area of the circle, and it should be less. You should never get anything that's greater than the total area of the circle, because that would be weird. The shaded sector is a pretty big chunk of that circle, so 72 pi does make sense. And then on the other circle over here, we got 24 pi, and the total area is 144 pi, and our central angle is only 60 degrees, so it's a kind of a small part of the circle. So 24 pi also makes sense. So you can kind of look at this logically and see if you did it right. Okay. All right. Number 3, it says the area of a sector of a circle is 120 pi square meters and has a 108 degree central angle associated with it. What is the radius of the circle? So this is, again, a backwards problem where we do our central angle over 360. That's going to equal our sector area over the total area. When you see a problem like this, because we've also done one with arc length, it's really important to see what you were given. Were you given arc length, or were you given sector area? We were given sector area, okay? Area of a sector. So that's going to go on top. And then we have our 108 degree central angle. That's going to equal 120 pi over, and again, we don't just want to put, like, we don't want to do A for area. We actually want to put the whole thing because our area consists of more than one thing. All right, our pi's cancel. So I'm going to do 120 times 360. That's 43,200, and that's going to equal 108 r squared. I'm going to divide both sides by 108. And we get 400. So 400 is going to equal r squared, which means that my radius should be 20 meters. And I'm actually going to go ahead and move this over here. There you go. Okay, so for examples 4 and 5, we are looking for the area that is shaded. And this is one of those questions where you have to find kind of a weird area. If you look at this, it's almost like we want to know what the area of the crust of the pizza is, not the whole pizza slice. So when you look at this shape here, you actually have two shapes, okay? You have, let's see, you actually have the area of a sector. Okay, ignore that line that's right there. We have the whole piece of pizza, crust and everything included. So we have this sector area. And what it looks like happened is we had this sector, okay? And what eventually ended up happening was we had this whole pizza slice, and then somebody came in and was like, you know what? I'm going to remove this triangular piece from the sector area, and that's how you get that crust. So what we have to do is we have to find the area of our sector and the area of our triangle and subtract them from each other, okay? So we're going to be doing two things. We need to find the area of our sector, the area of our triangle, and subtract them. So sector area is your central angle, which for us is 90 because we have this box here. So it's 90 divided by 360. I'm looking for my sector area, and that has got to be out of the area of the whole circle, which is pi radius squared. So this is going to be 90 over 360. That's going to equal x over 36 pi. And now I can go ahead and do 36 times 90 divided by 360. And that's going to get me 9 pi. And I'm just going to circle that. Okay, that's all I want right now. Then I have to go back and find the area of my triangle. This is a really nice triangle because it is a right triangle, which means that I already have the base and the height. So as a reminder, area of a triangle is base times height divided by 2. Both of these links right here are the radii of the same circle. So that means that this side over here is also 6 meters. So this is going to be 6 times 6 divided by 2. And that is 18? Yeah, this is going to be 18. Not 18 pi, just 18. And then I have to subtract those things from each other. Problem is, those are unlike terms, so I can't actually subtract them from each other. So my shaded area is going to be 9 pi minus 18 meters squared for that first shape. Number 5 is actually the same thing. This triangle is just going to be a little bit funky. So we need to find the area of our sector, the area of our triangle, and subtract them from each other, okay? So we've got our 60-degree central angle over 360, and that's going to equal our sector area over pi radius squared. All right, so we've got 16 times 60 divided by 360, and I get 8/3 pi. I'm going to double check my math. 16 times 60 divided by 360. Yep, okay. And then area of our triangle is base times height divided by 2. I may have like the base of my triangle, but I don't have much of anything else, okay? Now, we've already talked about this. In a circle, your radii are going to be the same. So I know that this side and this side are the same. This is 4 meters, okay? That makes this an isosceles triangle, okay? So if that top angle is 60, I would do 180 minus 60 divided by 2, and I get 6. Ooh. Oops, sorry. 180 minus 60. I did divided by 20 instead of divided by 2. So actually, I get all of these angles are 60, which means that I have an equilateral triangle. And if I have an equilateral triangle, I can actually do side squared, square root of 3 over 4. So this is 4 squared, square root of 3 over 4. 4 squared divided by 4 is 4. So this becomes 4 root 3. And then I subtract those two things from each other. So we have 8/3 pi minus 4 root 3 meters squared. And that is how you would find the area of like a shaded area. There you go. All right. We have talked about different types of geometry in geometry. Back in unit, unit 2, so a long time ago, we talked about this thing called taxicab geometry. And in this unit, in unit 2, in this particular topic, we talked about how there are multiple types of geometry out there. The one that we use most of the time in this class is Euclidean geometry, where everything is on a flat plane. And, you know, you can move any direction to connect points. When we talked about taxicab geometry, everything was on a flat plane, but we could not move diagonally. We could only move horizontally and vertically to get from one place to another. However, I would say probably one of the most like naturally occurring geometries are spherical geometry, which we're going to talk about now, because essentially the Earth is a sphere. It's not quite a sphere, but it's essentially a sphere. And instead of a surface being a flat plane, now our surface is the surface of a sphere. Okay, so here we go. Euclidean geometry. In Euclidean geometry, a plane is a flat surface that extends without end in all directions. A line in the plane is a set of points that extends without end in two opposite directions. There is exactly one distance that can be measured between any 2 points. This is in Euclidean geometry. In spherical geometry, a plane is the surface of a sphere. A line is defined as a great circle, which if you are in social studies, you've actually talked about great circles, or you will be talking about great circles, which is a circle on the sphere whose center is the center of the sphere. There are 2 distances that can be measured between 2 points: the lengths of the major and minor arcs of the great circle. So if you look at this first image here, this is a plane in Euclidean geometry. It says plane P contains line L and points A that are not on the line. And then over here we have a sphere that contains great circle M and point A that is not on M. Great circle M is considered a line. So a line in spherical geometry is a circle, and a line in Euclidean geometry is a line that we are the most accustomed to. Okay, so one thing that I need to point out really quickly is I could put a point here and a point here on my great circle. I can call this T and V. And I can say, how many lines can I draw to connect points T and V? Well, I can draw this line to connect points T and V, or I can draw this line to connect points T and V. So in a sphere, in spherical geometry, instead of only being able to connect 2 points with one line, you get to connect 2 points with 2 lines. And again, these are the major and minor arcs of circle. So number 6, it says the diameter of the sphere shown is 15 and the measure of arc AB is 60. Now, it says find the distances between A and B. So it tells me that the diameter is 15. So that means that from point A to point C, that is a diameter of 15, which means that if I'm looking at the radius, which that point should be there, that's going to be 7.5, I think. So this is 7.5 and this is 7.5, okay? And then it gives me the measure of arc AB. This one right here is 60. And I know that it's the minor arc because it's only got 2 letters in the name. It's not arc ACB. Now it says find the distances between A and B. So again, I can go this way between A and B, or I could take the long way around where I go all the way to C and come back all the way over here for B. Well, those are arc lengths, okay? So what I'm going to do is I am going to start with the distance, the short distance from A to B. And then I'm going to do the long distance from A to B. So here's the short distance, and here's the long distance. All right, and again, it's just arc length. So I have to do my central angle, which is 60 degrees. I guess I should have talked about this. I should have kept this in those notes. But the distance from whatever your arc length is, it's going to be the same as the central angle. So because this is arc AB is 60 degrees, its central angle is 60 degrees. So 60 over 360 is going to equal my arc length over the circumference. Circumference is 2 pi r, so this should be 15 pi. So we've got 15 times 60 divided by 360, and we get that the short distance is 2.5 pi meters. And then the long distance would be 300 is my central angle over 360, and that's going to equal x over 15 pi. So 15 times 300 divided by 360 is 12.5 pi meters. And then if we were to add these two things together, 12.5 plus 2.5 gets me 15 pi, which is the total circumference of my circle. Anyways, that's all I have for you. If you have any other questions, please go see your teacher during their normally scheduled tutorial times, and I will see you in the next video. Bye.